So it's my great pleasure to welcome Cherie Kagan to Shift for the first time. So Professor Kagan is the Stephen J. Angelo Professor of Electrical and Systems Engineering, Professor of Material Science and Engineering, and Professor of Chemistry at the University of Pennsylvania. And so we're looking forward to your talk.
I want to start by thanking both Jorge and Ferenzo for the invitation to be here. I also want to thank you for sharing your architecture, your geography, your culture, your food, and to everybody for sharing your science. It's been really a fabulous week, and I'm so happy to have been here and get to participate in SHIFT. So I wanted to tell you a little bit of a story today. I'm going to talk about colloidal nanocrystal materials. And thinking about them, only today I'll focus on optical devices. We like electrons too, but optical devices. And I'm thinking about what's different about colloidal nanocrystals that allow us to create both materials and structures to realize different types of functions. And today you'll hear a story that's done in a collaboration with a number of my colleagues, Chris Murray, Nader Ngeta, Kevin Turner, Troy Olson, Mark Allen, Vijay Kumar. Anyway, you'll see Andrea Liu, Nick Katov. You'll see it as I go through the talk and try and introduce all of my students and sort of giving this to you as a little bit of a story. And of course, we thank our funding agencies and hope they continue in the current climate in the United States. You've heard a lot about nanocrystals. Today, I want to just share with you that most of the nanocrystals I'll talk about today are all going to be on the order of about 5 to 10 nanometers in diameter. They too, of course, those shies, they would show shape-dependent properties, all kinds of characteristics that we appreciate from colloidal nanocrystals. Today I'm going to tell you a story too where as we synthesize most of these nanocrystals, they're typically grown in solution, right, in flasks as chemists where we have ligands on the surface. And today a big highlight of the talk is what you can do by controlling surface chemistry that's going to enable a lot of the characteristics that I'll tell you about. And on the right, I've shown we, as a community, we can make lots of different compositions of nanocrystals. Today, in the context of the talk, I'll choose 5. Maybe I'll leave out the magnetic ones. But we like nanocrystals of all different compositions to look at their different characteristics. And I'll sort of tell you this in the evolution and the story that I'll talk about today as we look at, in particular, the space of optics and optical metamaterials. So some time ago, when I was a student, we learned, as we think about, I like the examples we heard about earlier in the symposium of thinking about how you build complex materials from building blocks. A lot we heard about was molecules. We think the same way about how can we build more complex materials, but by using nanocrystals as the building blocks of materials. And so I'm going to focus today, while we also like single particles and learning from fields like Philippe's on thinking about quantum information science. Today I'm just going to focus on using nanocrystals as building blocks of materials. And many years ago we learned and showed that you could take colloidal nanocrystals and you could assemble them into solids, where in this example here each dark spot is at the inorganic core, and the space between this that's white that you see in the transmission electron microscope is actually the organic ligands that are on the surface. And we learned at some point how to make these into crystals. So the same way that you take atoms to build crystals, very similar models for things like terrace ledge kink and all sorts of things. You can build solids and crystals of nanocrystals. So today, and when we first looked at these in examples of semiconductor nanocrystals, you could see very weak interactions between the nanocrystals, things like in semiconductors like fluorescence resonance energy transfer. But today I'm going to tell you where we've come. I'm going to fast forward 20, 30 years, something like that, and tell you where we're going to go. So as I tell you the story, we like obviously lots of different compositions of nanocrystals. I won't talk today about nanocrystal synthesis, but obviously we'll make many of these nanocrystals using the wet chemical techniques that many of us enjoy. We'll think about using these as building blocks of materials. I will tell you some about, in particular, how we use surface chemistry in the design of the materials themselves. And if we do this, you can think about materials and sort of, if each of these are 5 to 10 nanometers in diameter, we stack many of these and are interested in collective properties on sort of the mesoscale. But if we could keep going, we can then think about how do we use this at the next length scales. And today I'll tell you about examples of what we refer to as superparticles, but larger scale structures that can be hundreds of nanometers to micron scale. And if we can make one of these, then we can make many arrays of these, and this will lead into a story about optical metamaterials. And when we think about using nanocrystals, I like to think about, well, why are we using nanocrystals? What do we get that is different in nanocrystals that affords us some interesting physics, capabilities, chemistry, right? What can we do with these? And so we like to think about what's unique chemically, mechanically, electrically, optically, thermically, magnetically. Having one foot in an electrical engineering department, even though I grew up and studying materials and working for chemists, we like to think about the opportunity where we design materials from the nanoscale all the way up to the microscale. We do this in electronics too. I won't talk about electronics today. I'm just going to tell you this story about optics where we really have the opportunity to control and mix different materials all the way across length scales. And we're interested, and I thought this was appropriate for this symposium on light and applications, but really in thinking about the opportunity where we can sort of mix characteristics. We like, if you have a stimulus in one domain, we can realize a physical property in another domain. So this is a characteristic. Often in electrical engineering, they show 2-port diagrams, show 6. But the idea that we can sort of mix across these domains. So I'm going to try and tell you a little bit of a story where I'm going to start with one example that's very more fundamental, leading into materials and physical characteristics. And then at some point in your career, you decide that, well, if I've been working on these for some time, maybe we could do something with these. And so time permitting, I'll tell you a little of a story about an application that we're looking at. So I'm going to start with the example of looking at optical metamaterials, a field that I learned when I first moved to university a number of years ago. And so we're really going to think about, and today I'm going to focus on examples that are chiral. You can see in the image, you can see things that fold like this. And so I'm going to tell you a little bit about how we get there and why, and the opportunity that comes from using nanocrystals that maybe perhaps provides an advantage compared to doing these in bulk materials. And so I'm going to talk to you about how we think about building optical components that are very thin and controlling all sorts of characteristics of light, and that could have applications in many different application domains. Oops. Okay. So what's different about nanocrystals? I'm going to start with metals. It's an easy way to understand the characteristics. If you think about, we can make metal nanocrystals. We've done the same thing with gold, silver, and copper. I'm showing 2 out of the 3 here. But if you look, for example, and you take gold nanocrystals as they're synthesized, in these examples, they have organic ligands on the surface. And so again, you can look at an electron micrograph, and you can see that you have the inorganic cores. And all the white space is, in fact, the organic ligands, right, that are separate them. And if you look at these materials, and this is gold and this is copper, for example, but if you look at these materials and you even measure their DC resistivity, it's above what you can measure in your characteristics, and somewhere above 10 to the 4 ohm meters. Right? It's very highly resistive. This is true in semiconductors from years ago as well. And what you can find is that these ligands will act with a separation of 1-2 nanometers, act as a very good barrier to electron transport. And so what we do think about, again, as I said, this is really an opportunity for surface chemistry. One thing that's possible in nanocrystals is that we can really go in and address what's at the surface. We can take one, we can swap it for something else. And so in this example, one of the ones that we like is these short, compact inorganic salts. So the first example, we use ammonium thiocyanate, ammonium chloride, lots of different salts. But if we do that, what we can do is we can swap the ligands that are here on the surface for something new. And if we use some of these compact inorganic ligands, the particles become much closer together. And depending upon the material that we make them from, in some cases, they just bring them close together. In some cases, particles will actually start to fuse together. And in other cases, they'll really grow into grains. And so you can see in the case of gold, in order to look in the electron microscope, we make a monolayer. And when these come together, right, obviously you get void spaces where the lost ligand volume comes from, but you can see that the nanocrystals start to fuse together. If you look at it in a multi-layer film, it looks like a gold film with lots of holes in it, right, empty spaces. You'll see in a moment we like to call these diluted metals because there are fewer atoms to contribute electrons to the characteristics of the material. If you look at copper, for example, similar to silver, those atoms really like to diffuse a lot, and they'll grow into polycrystalline materials. If you look at the DC resistivity for any of these materials will drop by 10 or even 12 orders of magnitude. And so you can see in the films here, this is gold, silver, copper. It really drops in DC resistivity. It gets close to what you measure in an evaporated film in the lab. Obviously, those are polycrystalline films, and get within a factor of 3 to 10, depending upon the composition of material. And so we can make very good conductors out of these materials. I won't talk about those today, but we do that. There's a whole component where we're working on RF electronics and the opportunity to build devices using these kinds of materials. One of the things that we were interested in at the time that we actually started looking at the characteristics of these particle systems was actually their optical characteristics. And so if you look and think about a system that looks like this, where again, it looks like an insulator, right? Very highly resistive at DC. At optical frequencies, it also looks like an insulator. And so if I show you if this is the real and imaginary parts of the dielectric function, if you look at the black curve here, you see that it's everywhere positive, consistent with it being a dielectric and insulating material, even at optical frequencies. And this is something we know fairly well for particle systems. If you look at these and you start to bring these particles close together, what happens is you can sort of dial in the dielectric function, right? You can, as you bring them closer and closer together, which we can do by control of the concentration of the ligand that we swap, you watch the real part of the dielectric function slowly go from being positive to everywhere negative, characteristic of a Drude-like metal. In the case of gold, you can really dial it in someplace in between where you have still holes in between. And so, for example, we like this because, so this is bulk gold shown here, and this is, for example, when we do this complete ligand exchange process. In the case of gold and silver, it'll really get very close to bulk gold and silver because it diffuses very much. If we anneal gold, afterwards, it'll also become polycrystalline gold. And so we've played around with these ideas of how do you dial in the real and imaginary parts of epsilon. We've done it to make, you say, would you ever want to stop someplace in between? The answer is yes. We showed that you could make very thin optical absorbers if you stopped somewhere in here. Today, I'm not going to focus on that example. I'm only going to tell you the story where we just use it as a way to make a highly conductive metal and a good optical scatterer. So we really take this ligand and we make it something that acts as a metal. And so, we know a lot about gold particles here. We first started in these directions where we also use imprint lithography. So I'm going to sort of match both assembly processes and sort of top-down fabrication techniques and sort of give you a mix of why you might like both. So we often use imprint lithography. We started where we imprint into a resist. And you can then deposit the nanocrystals as in solution, as colloids. So we cast them on the surface, often just by using spin coating. And then once you do that, you can just immerse it into this solution of this ligand for something like 30 seconds. And what happens is those particles come together, they become good metals, and then the characteristics that you get depend on the geometry of the printed structure, no longer individual nanocrystals. If you didn't do the ligand exchange, it just looks like the individual nanocrystals. So each one of these rods here is then gives a characteristic. It looks like the dielectric function of that characteristic of gold, but it depends on this, the geometry that we print. And so in the early days, we were interested in this idea, could you build large area optical metamaterials? And so these processes were commensurate with those ideas. We were interested in tuning dielectric functions, but if you look here, what we did, this is an example where we showed that you could take these processes and build quarter wave plates. And so with our colleague Andrea Liu, he designed this structure here where the rods in the vertical and the horizontal direction are slightly different in dimension, and that means their resonances are slightly detuned spectrally. Right, so you get a resonance for one and a resonance for the other, but in X and Y they're detuned, and in between those two resonances you get a 90-degree phase shift. And so it's that requisite that requires you to then get EX and EY off by 90 degrees, and it lets you to make a quarter wave plate. So what we did was we prepared circularly polarized light, and we looked at the transmitted light and analyzed to see how linearly polarized the transmitted light was to characterize it as a quarter wave plate. So in calculation, you get the red curve, and experiment, we got the black symbols here. You can see we have imperfections in our structure, so we're not quite as perfect, but it was pretty good, and we could even play around with geometry and make very broadband quarter wave plates. But today, instead of telling you about 2 dimensions, because 2 dimensions you can also do often by top-down techniques, there are some advantage to these, but today I really want to tell you about how it enables us to make structures in 3 dimensions. And that's hard to do in fabrication. If you do it in fabrication, it's usually brute force. You know, you print one structure, you do a lot of lithography, you do one structure, then another one, another one, another one. So you effectively make something that looks 3-dimensional. But today I'm going to tell you about examples where we use 1 step in lithography and we use chemistry to drive folding in 3 dimensions. So I'm going to give you some examples where we make structures that look like the structures I showed you at the front, where we can make structures that fold in 3 dimensions. We can make them out of lots of different types and compositions of nanocrystals. I'm going to show you a few examples today. What I won't have a chance to tell you is you can actually also release these structures from the surface and suspend them in solvent. And we've played games with how you can manipulate them with acoustics or magnetic fields, or we're playing right now with optical trapping as well. But the key to this is to really think about, if we put a nanocrystal layer on a thin evaporated film, for example, we think about what's different about nanocrystals from the evaporated film. And that allows us to really address the nanocrystals, and the bulk film underneath doesn't care. So I'm going to tell you through this in just a moment here. So if we take we started with the example where we made the evaporated film titanium. We've since got a little bit smarter for adhesion reasons to change the metal underneath. But we put down a layer of nanocrystals. And as I showed you at the beginning, if you look at the nanocrystals, they have ligands on the surface, and that provides some separation between those nanocrystals. And if we take them and made rods and we released them up and studied them in electron microscopy, we have a thin titanium layer here, and this is the layer of gold nanocrystals. And I won't say it's completely straight, but it's kind of straight. Okay. But now if we take these structures and we immerse it in a solution of this more compact ligand, what happens? All these particles want to come close together, right? And what it does is that it creates a compressive strain in this nanocrystal layer. And when it's juxtaposed with a bulk film, it creates a misfit strain at this interface. And what it does is that it causes all of these structures now to curve right in the direction of the nanocrystal film, because we have this compressive force here. And you can get these structures to fold. And we then went and studied mechanics, not as mechanical engineers. And so, but what we did is we made many structures where we controlled, for example, the thickness of the titanium layer. And as you can see here, as you make the titanium layer thinner and thinner, you can see that these structures curve more and more. And so we could this is an equation that's for a mechanical model for a bilayer, where you can, and it looks kind of messy, but actually there are only a handful of actual physical properties. What you're measuring is so you have the thickness of the total structure and that of the titanium film, for example, how much there is. That you know and you can measure. The curvature is what we measure when we go and release all these structures. We can calculate what this curvature is. The only other things that are actually in this equation are the Young's modulus of the nanocrystal layer, which we don't know. In this case, the Young's modulus of titanium, bulk titanium, which we do know, and then this thicknesses that we measured. And so we made a lot of these, and could do statistics on them and fit this to a model. And what we could learn from this as an upshot is that just by simple chemical approaches, 30 seconds immersion in a solution, for example, we could generate strains, misfit strains, of about 6.5%. That's 10 times more than when you heat a copper steel bimetallic strip by 1,000 degrees. The other thing we could learn about is Young's modulus of the nanocrystal layer. And you can see here these materials are actually quite soft, right? Originally, and so consistent with this idea that you fold them. And actually, if you anneal them, we could go further, and you'll see that we could get even higher strains and such. But what we wanted to do is that we wanted to say, okay, so now we wanted to tackle this challenge of, could we make structures in 3 dimensions and only use 1 lithography step and do it over large areas? So we make a template to use imprint lithography, and it looks like a pinwheel. The pinwheel could be all in one direction or the other to make enantiomers. We imprint into resist. We can deposit for example, a thin layer of material by evaporation, for example, metal. We could spin coat our nanocrystals, and then once they're on the surface, we could do this ligand exchange process that really wants to bring the nanocrystals close together. And so these will then fold. We can also anneal them. If you anneal them, it'll drive sintering of the nanocrystals. It'll create greater strain. It'll create greater folding. So what you can see here, just as an example, by doing this, if we take the same sample, just make multiple samples, we can do this over and over again. And we just control the time of the ligand exchange, right? That's going to control how well we bring the nanocrystals closer together. You can see that we can control the folding of these structures. And now we've done this for many years in different materials, and we've gotten fairly well practiced at this. Okay, so this is where we started. The example was, could we use this as a way to create chiral metamaterials? And so what we did is we got a little smarter and put gold as the metal underneath, which creates much more better adhesion, and so it creates much more uniform processes and strain. But you could print, this is the two-dimensional structure of the pinwheel in one in concave, whichever way you like to think, pointing left, pointing right. And then we could build these processes, and you could do it over large areas, and each one of these structures would fold. And then to characterize these over large area, what we did is that we would prepare circularly polarized light. And if the direction of the handedness of the circular polarization matched that of the direction of the folding of the arms, then you'd expect the transmitted light to be reduced. And if you had the opposite handedness, then it wouldn't reduce the transmitted light by as much. So the characteristic that we look at is how different is the transmission of light when we illuminate with right versus left-hand circularly polarized light. And so that's what we call delta T. It's very similar to what you've seen for MCD or other things as characteristics of chiral materials. And so what you'll see here is that we made the two different enantiomers, left and right enantiomers. And so you can see about 0, they're mirror symmetric, right? So they should have the flipped polarity of the response depending upon for light. And so if we don't anneal these structures, you just use the ligand exchange, we see the dashed lines here for the two enantiomers. If we anneal at low temperature, these structures become even more metallic, right? Because they fuse to become polycrystalline materials. And so you see that blue shift, and we get stronger responses like you see here. And so we learned that we could do this process. Once you know that you can do it, you can sort of think about what you could do in design. And so we've played all sorts of games where we can control the number, the direction, the degree of curvature of all of these structures that we put on the surface. This is an example where we made some arms that point left, some point right. They're different in their length, so they're spectrally detuned in where you have their resonances, but you could make structures that look like this. This was our first attempt to try and make something where we could change it after we built the structure. So if we make it the structure, it has, we have the long arms and the short arms giving different polarity of response because they're pointing in different direction. If we anneal it, it'll all shift as they become more metallic. But once you do it, that's all you get because they form really good metal-metal bonds, right? We still don't get away from chemistry here. So we would make these structures. We made ones with different numbers of arms, different lengths of arms to try and make broadband chiral materials, which we did over time. But one of the questions we often got was, well, with nanocrystals, could you make them reconfigurable? And we would have loved to make them reconfigurable, but we really formed good bonds, and we weren't getting, as much as we could swap ligands out, once we form a good bond like that, we weren't going backwards. So one of the things that we did is that we also had, many years ago, worked on vanadium dioxide. So you can synthesize, and so in Chris Murray's lab, they developed the synthesis of VOX, a precursor to vanadium dioxide. So you could synthesize these materials. We heard about VO2 earlier this week. And so you can see that at room temperature, VO2 is an insulator. You see that electrically. You also see it in its reflectance. When it's an insulator, the reflectivity is low, like you think. And then when it goes through the insulator to metal transition, the reflectivity is high. And you can tailor that phase transition by controlling also the doping of the material. So you can do that in the synthesis pot. In a moment, I'll show you can actually do it after synthesis as well. But if you introduce dopants, you can just tailor the temperature at which the transition occurs. And so what we do is that we, again, do the same process. We can imprint onto the surface. we can deposit a metal, then deposit the nanocrystals, and then we can both do the ligand exchange and we anneal it in an RTA, and we can make VO2-based metamaterials. So this is an example of these same kind of folding structures, but now they're made out of the phase transition material. And so if you look at it again, we can make left and right-hand enantiomers, right, of these materials. And so what would you expect? So we built this system in our spectroscopy where we could heat this material through the phase transition temperature. So again, it looks like these structures are on a surface. At low temperature, they're in the dielectric phase, right? They're insulators. And so if you look now, these structures, we're looking out at long wavelengths. Remember that VO2, like we heard earlier, becomes plasmonic at longer wavelengths, pass around 1.5 microns. So what you see is that if you look and these dashed dots versus solid lines are just the left and right-hand enantiomers. So again, you see this sort of mirror symmetry across the zero axis. But if you look at it in the insulating phase, you can see some photonic resonances here. But if you then heat it above about 75 degrees, above the phase transition temperature, they become metallic, and you see the idea that you now have plasmonic resonances in these structures. And the one thing about this is now I can go back and forth. And so you really can create a system that's reconfigurable. I can just, by controlling the temperature, go back and forth and switch between the purple and the dark red curves. And so, for example, if we monitor at about here, and we monitor it over here, we just followed how that response to the difference in transmission of polarized light between left and right-hand circularly polarized light. And you can just follow it back and forth, back and forth, back and forth. And so now you can really make something that's reconfigurable, that comes from the idea that you've built these structures from a phase transition material. All right, so I'm going to give you now one more and ask, well, what else? Now we know we can do these with metals, we can do it with phase transition materials. I'll say we did it with magnetic materials too, but I won't describe those today. But we came back to one of our favorites, which is semiconductor quantum dots, right, where it all started. Oh, I forgot one slide. Let me tell you one slide before I tell you that, is that you can also mix the materials, right? If I take the VO2 and I could say, well, I did gold and we did VO2. Can we mix the materials, and is there a reason to do that? And that's one thing that's nice about nanocrystalline materials, is that these are all in the order of 5, 10 nanometers in diameter. Effectively, you create a new material which is homogenized on the length scale of light, right? You can, by mixing these systems. And so here we did some EDX to characterize and see if we mix these materials, you find the VO2 and the gold intimately mixed throughout the entire structures that we can build. And so we can build these out of mixed materials. And really what it allows us to do is to basically control the resonances in these materials. And so as we add more gold, we shift to higher energy or higher wave numbers. And so we could tailor the spectral position simply by mixing compositions of materials to sort of give us new effective building blocks from which to design these. All right. Here's my promise on semiconductor quantum dots. So again, it's the same process, right? We can imprint into these structures, and we can create three-dimensional structures from colloidal semiconductor quantum dots. And the question we were interested in here was to actually look and ask this question: could we create materials that showed circularly polarized luminescence, and would it offer us some advantage? Often the examples where people look at circularly polarized luminescence, the selectivity is very small, on the order of about 10 to the minus 2, right? You make a molecule that's chiral. You have a template that causes something that's achiral to have some handedness to it, right? And so we were interested to see, could we use this process, and would the geometry in which we put the nanocrystals give us a characteristic that would then give us circularly polarized luminescence? So this is a work that we're trying to finish now. But we built these materials from core shell quantum dots. So core shell quantum dots, obviously we can tune the color of their emission, but they also have, about, in the examples here, they have about 85% quantum yield. And so you can see here, this is just the absorption and the luminescence of the constituent quantum dots that make up the structures that we built. So that's these guys here. And then we can fabricate these into these structures, the same as I've showed you before. And so if you take these structures and you look at, this is just 1 minus the transmittance, but this is similar to the absorbance. What you'll see here is that if we shine unpolarized light, it's the curve in between, these structures happen to be right-hand circularly polarized that we use to consistently compare. And so we see something that's a little bit larger that comes from the excitation side. And you can see something that we think is related to photonic modes that are riding over the top of this spectrum. And then you can see that obviously right-handed is greater than left-handed in the extinction. If you look at in the luminescence, you can see here the luminescence compares that for right-hand and left-hand circularly polarized luminescence, and you can certainly see that there's a difference, right? And we're creating some dissymmetry between circularly polarized luminescence. So just to tell you where we are is we've made a lot of samples and done a lot of spectroscopy. In this case here, I'm only going to tell you, we've done some spatially resolved spectroscopy to try and understand these processes, but I'll tell you that if we illuminate these materials here, we're illuminating them with unpolarized light, and then we're characterizing, for example, how circularly polarized the luminescence is. And we could do that, for example, and that's just like the two spectra that I showed you before, but we can do that and also control the curvature of these materials. So each one just represents one building block in a very large array, like I've showed you before, and we can make many samples where we control the curvature or folding of these structures. And so we were interested in understanding, how does the dissymmetry factor, the difference in the left and right-hand circularly polarized luminescence, depend on the geometry of the structure. And so what we can see is that the dissymmetry factor does in fact depend, these are narrow arms, these are wider arms on these two curves, but these colors here just show you that we're controlling the curvature. And what you see is that it increases and gets close to sort of a maximum somewhere in there. And the lines that are running behind it are actually a mechanical model of how the height of these arms relate to the curvature, which is something that we've also done in the past. And so it's clear that they're related to each other. And so what and we've also measured how circularly versus elliptically polarized the light is that is emitted. But what we see is that we can create first materials that have very high dissymmetry factors. What we think is happening is that these are related to higher order photonic modes in the structures, and that what happens is that you sort of get a wave guiding effect of light here. I mean, these structures are bigger compared to lambda, the wavelength of emitted light, and we think that effectively that's what's giving rise to this circularly polarized luminescence, that they effectively look like waveguides hanging off the edge of this structure, and that's giving us the sense of geometry and the selectivity for the chiroluminescence. So this is something, we're working to finish now. So I thought with just a few minutes of time that I have left, as much as we love our physics and very fundamental science questions, we also decided that, at some point you said, gosh, what could we do with these materials? And we had an opportunity, and I direct, believe it or not, a center that's called the Internet of Things for Precision Agriculture. You could ask what I know about agriculture. The answer would be not very much, but I have wonderful colleagues who are willing to teach me. And so this center is about 25-ish faculty across different universities. So we have 4 partner universities, obviously at Penn, where we lead, but at Purdue, the University of California at Merced, and the University of Florida. And those both are selected for their technical expertise, but they also give us access to different cropping systems, whether it be row crops like corn and sorghum, or tree crops like fruits and citrus and pistachio and pomegranates and stuff like that. And so we really wanted, the idea behind this was to ask this question, could we tackle a big problem? We were interested in this question of food, energy, and water security. So I thought this was appropriate, given energy was in the title of the conference. And the question is could we build technologies for precision agriculture? Was it the right time? Not precision agriculture of 30 years ago, but the idea that, in both information technology and in data science, we've really come to a very new place. And so could we bring that to the agricultural space, where you have to realize what the requirements are for agriculture, right? It's an incredibly large area environment, right? You have huge fields. It has to be extremely low cost because the margins are very small, right? And then you have to build things that work out in these environments. And so the idea behind these technologies is to make what looks like a very busy field, whether it be for row crops or tree crops. Today I'm going to tell you about sensors. The closest, I live on one extreme of the center, even though I have to talk about the whole thing. But this is something that we were interested in. So if we want this depiction, of course, we had to put our work together as a group, and I'll just say I'm going to tell you today about an example of optical sensors, because this is a conference on light. But we bring together expertise in sensors, robotics, communications and energy technologies, and data science techniques to really do the full loop of how could you get information from the field. You know, it's like you looking at your plant and saying, oh, it looks okay. Oh, it doesn't look okay. You know, you want to know when a plant is stressed before it shows visible signs of being stressed. Otherwise, it's too late, frankly, right? And so the idea behind this is how do you get information that you can't see directly? This is where, if you know, chemists, very important, right? Because lots of things are, chemical signatures. Some can be physical signatures, but not, often before you see the leaves look like they're in a bad state. So I'm going to tell you a little bit about sensors that we've been trying to fabricate for these uses. Okay, so you can think about what do we want to do? We want to make sensors that we can really distribute across a field, and think about deploying them at large field scales. Could you even do it to the point where you put one sensor for every plant? So today, if you look, you can go, and I have pictures where we've gone to visit, the experts who work in fields. And if you want to buy a soil moisture sensor, it's often huge, and one sensor costs about $2,000 US. And so it's an impressive. If anyone wants to see, I'll show you a photo of a guy who's holding one of these things. But that means they put 1 in 100 acres, right? So if you think about how many plants that you have in that space, the challenge is you're terribly undersampling the field. But you can't afford to put more in there. That's the challenge. And so we wanted to ask this question, well, what if we could build sensors at the millipenny to penny kind of scale, or maybe even $1, depending upon what it is. And then how many sensors could you put out there to at least get information to know that a plant was being stressed? And so, there are all sorts of signatures that we're interested in that affect the health of your crops. Obviously, water stress, we know that. We all water our plants. But temperature, volatile organic compounds that are often signatures can be biomarkers of some kinds of disease. Nitrogen, phosphorus, and potassium are our nutrients, right? We need to know about those. Pathogens, unfortunately, especially these days, are impacting the health of our crops, and obviously pests are a problem. And so one of the things that we've been looking at is certainly there are lots of off-the-shelf components that you could think about building sensors, but we wanted to ask these questions about what could you do with materials, right? And so I'm going to tell you today about optical sensors that we're building. We also work on RF electronics that you can bury in the soil. No light's getting into the soil, so we have to go to much longer wavelengths. All right. So I'm going to tell you about leaf sensors. And this is an example where you can think about, we can instrument lots of existing farm machinery, or obviously introduce robotics that can carry whole suites of cameras that are being used today. In fact, we saw, right, as we went on the excursion, when we stopped at La Esperanza, there was a gentleman who was flying drones to what I assume was mapping the landscape below, and then we brought the drone back. He had to change the battery out. This is one thing why we work on batteries, is because you have to change the battery out. He put in a new battery and he started again, right? But it really gives you an opportunity to map landscapes, right, at the scale that we're talking about. Well, if you could put sensors there, then the robots could also not only map the landscape, but map the sensors as well. That's an example. The other things that are deployed is obviously you put lots of farm machinery is regularly going through fields, and you also have things like walkers or center pivots that are moving through the fields. And my colleagues at Purdue University really want to instrument these with all sorts of cameras, right? Those components are not so difficult. And so what we've been doing is basically building dielectric metasurfaces, and we're we have ways that we want to basically be able to sort of spray deploy these onto, make them small enough so we could spray deploy them onto plants. And then to go by, and so you can see we can recognize them here, but we want to go by and be able to characterize those sensors and then use them as a way to characterize a particular target of interest that will teach us about the health of our plants. And so just to give you, I won't say very much about this because this is more of a robotics problem, not a materials problem, but an example is that we have various robots that, that are equipped with all sorts of cameras and illumination sources. These robots can operate autonomously, and so here we've been slowly going to more complex environments, but the robot can autonomously navigate through a set of crops. And it can both first use an RGB camera and say, I can find the sensor, and it finds the sensor. And the first one, we have it using a hyperspectral imaging camera, and it can actually measure the sensor that we have stuck onto a leaf. And so we've started with hyperspectral cameras. We're hoping we can get to only multispectral cameras from a reason of cost. But this is an example where we're starting to build the kinds of capabilities both in hardware and software to be able to navigate and measure sensors. So there are lots of ways to think about how to design a sensor. Leaves, by the way, what often people do is they take a hyperspectral camera, and as a leaf moisture changes, you can measure subtle changes, particularly out at longer wavelengths, in the reflectivity of the leaf that will teach you something about the water. It's not so convincing how different it is. You're really using that based on intensity. It's not my favorite choice to just choose intensity. I'm going to tell you today about designing colorimetric sensors. That's easier to understand. I will tell you we're also working on polarization selective sensors as well, because it gives you a great way to distinguish the sensor from the leaf. And it also can have very good and big changes in polarization as you transmit through a metasurface. But I'm going to tell you this one because it's what I have time for and perhaps easier to think about. So we think about designing high Q dielectric metasurfaces. We need them to be, because if you can imagine, if you want the resonance to be sharp so that if it shifts in wavelength that you can distinguish one from the other, so that's where the high Q is important. You want it to be sensitive so that it shifts a lot relative to its width to make it easier to detect. And this resonance has to have a large enough reflectivity so that the robot with the camera can actually go and see it. So I will tell you we got better at this over time and looked at different processes to do this. And so we characterize a figure of merit as sort of the product of these three in the design of the sensors that we create. All right, so we first started by building home-built instrumentation. One thing we had done many years ago, which I didn't talk about, was that when we first developed the gold and the ligand exchange process, we also developed an imprint process where we could directly imprint into the colloidal dispersion. No resist involved, no traditional lithography, and that's possible. And so what we did is we went back and did this now with dielectric materials, and so we did this with titania nanocrystal dispersions. We choose titania because it has a large dielectric constant. We can imprint into the resist, and then depending upon the pressure, we can either leave behind structures that are patterned that have a little bit of a residual layer underneath, or if you press hard enough with enough pressure, you can leave no residual layer underneath the structures. Interestingly enough, what I'll tell you is actually we like this structure with the residual layer and for reasons of optics. But we learned that we could do this over very large areas. We've since moved from our home-built machines, for which we started to have all these clones, and then bought a commercial one and decided that was a better way to go. But you can print on rigid, plastic, all sorts of substrates that you might want. And the difference is that if you have structures that have this residual layer, you get these higher Q resonances, like you can see here in blue, compared to this one here when you have no residual layer, that you see very little. So if you wanted to get good dielectric resonances, you got to make structures tall, right? But if you have this underlying residual layer, you don't have to make it as tall, which makes it much easier in fabrication and polystability. And so why is that if you think about this, this is where we get the high Q from, is that if you have this residual layer, that residual layer acts as a waveguide, and now you generate what are known as guided mode resonances. And so the idea is that we have these pattern structures. Those pattern structures will scatter the light into the waveguide. The waveguide then gets trapped within that waveguide structure. And then what happens is that you can also think about it as a selectivity in Q, right? That you basically have to match the diffracted modes to the resonances that can be sustained or supported within the waveguide structure. And so these structures give us high Q resonances. So that's one thing that we wanted in order to basically build these sensors. The next thing we wanted was high sensitivity. And so what we did is that at the first start, we actually mixed the nanocrystals with an adaptive polymer. In this case, we started with chitosan because it's a moisture-sensitive material. And we can also do the imprinting into these composite mixtures of organic and inorganic materials. And we could contune their relative compositions. And we found that at one particular composition, right, we could get the largest shift between, say, a low humidity and a high humidity state, right? So we could get the biggest sensitivity. And then we chose that, and you can see that if we cycle in time and we increase the relative humidity in a chamber that we built where we can also do spectroscopy, you can see that that peak position, as we turn it on to, from 5% to 10%, 5% to 20%, and so on, we could go between a low humidity state and a relatively higher humidity state, ways that we often look at sensors, right, as we increase concentrations. And you can see we could really map the peak position that this resonance here. What happens is if you look at the resonance here, what you'll see is that that resonance shifts as you see different amounts of moisture, right? And so you're really just getting that resonance just changes color. The one thing is that we so far had high Q and high S, but the reflectivity in our first structures was kind of small, and it was hard to see in real environments when we sent the robots out. Perfectly fine in our spectroscopic techniques in our lab, but that wasn't the challenge where we had it. So the most recent structures that we're just finishing some work on now is that we actually switched to using UV curable titanium inks. You can imprint into those. Underneath that, we put a layer of this chitosan, and after we imprint, the imprint ink actually has a whole bunch of organic molecules, right, to make it UV sensitive. So we do this ligand exchange process, and it removes the organic components, which we can follow using IR spectroscopy, and makes a nanoporous material. And then if we heat this, you can get what's known as capillary infiltration. And if you go above the glass transition of the temperature of the chitosan will then diffuse into the pores of the structure, and now you get this mixed system here. And we're just following it. Here's the chitosan. Here, this is just a blank layer of chitosan and titania. Then we imprint into the titanium. Then we do the ligand exchange. That's here. The chitosan's still here. And after we anneal it, you can see the chitosan layer underneath is almost gone. It's all basically infused. And you can study that both chemically and spectroscopically to show that that's the case. And the nice thing about this is we can do this over a large area. The reason for also choosing dielectric metasurfaces is our light from the sun will still come through. This is mostly transparent except for where our resonance is. And that means that we don't disturb the photosynthesis and processes that occurs in the leaves, but you can make these on rigid and plastic surfaces. And now these structures have large changes. The magnitude of the reflectivity is large. So I'll just tell you this last story. Here's an example. If you put one of these sensors at 5% relative humidity, and then you put it at 85% relative humidity, you can see the shifts in the spectra as you go. If you look at it and you put one of these, this is the reflectance of the sensor. This is what the reflectance of a leaf looks like. And so you can really pick out now the sensor from the leaf. And what we did is that we put the sensor on the leaf. And what we did is we let it equilibrate on the leaf. For example, as it equilibrates on the leaf, you see it shift. And that's because when you put it on the leaf, the moisture from the leaf actually creates a very high humidity state that the sensor sees. So now we have to put this on the leaf. And what we did as a first test is that we took a leaf, and it's now sitting at this state here. And if we cut the leaf, what happens to your leaf, right? It loses its water over time. You can actually characterize that by a technique also called porometry. And you can watch over time as the moisture level in the leaf drops once it's using the sensor. And all we're doing is just doing spectroscopy and monitoring that peak over time. And so we can use it as a way to measure our techniques. And now we've deployed these now to California, to Indiana, and we're trying to now measure these out in agricultural fields on things like corn and sorghum and some pistachio trees. All right. And so maybe what I'll do is, I think I'm probably out of time, I'll stop there and just tell you, there's lots of things to do with nanocrystals that makes them different. We like all of them, and think about, from our fundamental chemistry and physics, maybe how we can do something that's interesting, both interesting technologically and ultimately, perhaps, hopefully important in society. So with that, I'll stop, and I'll be happy to take any questions.
Thank you. Time for some questions. Please, Oscar.
Thank you very much for the very nice lecture. It's just a curiosity. The term that you used, the meta-atom,
Yeah.
it means an atom in an excited state or
Oh,
something?
I see. No, it means one of the building blocks of the large area surface. So when I showed, these structures that fold. When I showed these structures that fold, right, and I showed you one, that's the meta-atom, sort of the building block of, then you make lots of them over a surface, and that's the metamaterial. Yeah, sorry. So that would make, this would be the meta-atom, the one of them. I apologize. I didn't think it's a term we just use all the time.
Yes, okay. It's clear now. Okay, thank you.
Yeah.
Thank you, Oscar. Questions?
This is when you
Unfortunately, think.
Yeah, thank you for your presentation. Wonderful. Related with the circularly polarized luminescence for the nanocrystals, you mentioned the symmetry factor, which was I could see around 10 to minus 1. Is this correct?
Yeah, about 0.3, 0.2, 0.3. Yeah.
Okay, but then for further practical purposes, brightness is usually considered. So that means absorption coefficient, fluorescent quantum yield, and so on. As a whole, how these materials behave?
Yeah, let's see. They have very high quantum yields. You can reach near unity quantum yields. That's why you can buy quantum dot televisions today, right? So this is perfectly reasonable to get very high quantum yield materials. And you can have things that have good high absorption in these materials as well. For us, I would say that the one piece that we're looking at now, too, is controlling the curvature. Actually, we can also make things longer. And so we have the next challenges to see whether we can improve. A lot of the improvements that we want to make are actually geometric in the structure that's folded.
Although not necessarily, because you can increase the curvature and the results could be better or not, depending on the vector.
Depends what it is,
Yeah.
but yes.
So
Yeah, but we have some results.
okay. Okay. Thank you.
Yeah. Yeah. The other thing we can do is, we build all these things with this large center pad in here, and that's not chiral. And so if we reduce that, then the dissymmetry gets. So we did some, even if in the same structures, we did spatially resolved spectroscopies, because that's what we do anyway. But you can see that if you look and illuminate just an arm, you get much higher dissymmetry factor. Yeah, you get rid of the achiral component.
In a sense, could be a good option, maybe.
Yeah, could be a good option. I agree. Yeah, yeah.
Yeah, first of all, thank you for a beautiful and insightful talk. I would have a follow-up question on that, because using quantum dots with and seeing such high dissymmetry factors, even though you talk of an electric dipolar transition, is quite surprising. Huh? So this is probably only an environmental effect based on the metamaterial, those.
Yeah, I think that's right,
metamaterials.
because the quantum dots themselves, we measure as a control, right?
Yeah.
They don't have any circularly polarized luminescence.
Exactly.
It's coming from the geometry of the structure.
Okay, and now the question would be, what if you changed the type of the quantum dot material, for instance, if you opted for chiral perovskites, for instance? So if you really used perovskites with chiral cations, would that even...
So you can do them with quantum dots too, which we've started. Okay, yeah.
Yes.
So we've thought about whether you can amplify these effects by mixing not just geometry but molecular components, and so we do have those, and we've actually begun those measurements as well.
Okay.
Yeah.
Okay.
Yeah. It's fun.
Thank you for the very interesting talk. I had a question about the use of the meta-surfaces. So do you need to shine light, I mean, for them to be efficient at specific angles, or can they work on a broad incidence?
So it depends on the material, right, and which one we made as to what. Certainly, like the last one, the last examples, obviously it's relying on diffraction, so there's an angular dependence to them. If you choose the shape and periodicities, you can make ones that are angular independent, but then they don't have as large a Q, right? So it's possible, but there are trade-offs. In the last example, we actually want to use it as a feature of the measurement, right, to be able to, because you could imagine, so we've actually built some models, and actually we have imaging that can go in and see it, and then, you can imagine, like, if you looked at a projection of what was a square, right, if the sensor was a square, you could look at the projection, you might know what angle you were at. We also have another way that we can have an internal standard to actually know and correlate to better account for angle. But that's something, yeah.
So you mean that if you have the sensor on a leaf which may move,
yeah, that's
can
right.
have any kind of position, that's not a problem, or?
Right. So it's an interesting question, right? So what we've been doing is to look at, for example, how do we account for the angle dependence? We also have a way that we can create something that allows us to account for it. Yeah, we have a device architecture that allows us to do it. Yeah.
Thank you.
Yeah, but we worry about angle for sure. Yeah, it's for sure.
Thanks for the great talk. I love the chiral synthesis by this ligand exchange, but I'm struggling to understand the mechanism, because I would expect just sliding of nanocrystals when you exchange the ligands. And if they just slide along the surface, I wouldn't expect bending. So are they somehow bonded to the surface?
Yeah,
or?
so we have to make sure they have some adhesion to the surface, right? So when we put gold nanocrystals on gold, you can imagine that when we do the ligand exchange, you probably get some okay bonding to them. But so let me give you an example first, and then I'll tell you about, we carefully select the surface so they don't delaminate, we don't lose them, okay? So some examples, we also do put self-assembled monolayers on them so that we don't lose the particles when we do the process. But if you look at it, and this is something we said all the time, is that you can actually look, if you have a layer of nanocrystals, if you do this ligand exchange, you can actually see, even if you have a film, you can see the whole thing shrink together, right? And that's happening this way, that's easy to see. It's also happening this way. And but we do select that surface so we don't lose them, so that the nanocrystals aren't doing their thing and saying, forget it, and I'm leaving, right? We've fought through the examples where we had delamination, and so carefully choose the composition of the material. And in some cases, we introduce a self-assembled monolayer to increase the interaction to that surface so that we do create that misfit strain and we don't lose the nanocrystals.
Yeah. Okay, thanks.
Any other questions?
Can you change the ligand in somehow different way? For example, using these optical switches which we heard on the first day to change the angle of this optical or some other?
Yeah. So this is something we're very interested in. We have the ligands to do that. We work with our collaborators in the Murray Lab, who's made some of those. One challenge, and so we've also even just been fundamentally interested, if you can bring particles closer together and they fold this way, could you make particle that put ligands on that further them apart and have it bend in the other direction? So in principle, that should work. In practice, we just have to find the right kind of orthogonal chemistry so that we don't end up with particles in solution. So we haven't yet found the right sort of orthogonal chemistries to do that. We only tried a little bit early on, and we haven't come back to it but it's certainly a very interesting area. The one you just have to not lose you have to be able to choose the solvents and ligands correctly, so you don't end up, the particles have to stay on the surface to get them to bend. Yeah. And then you could introduce ones that have, optical switches and things that would change. And so those you can do in assemblies, and we've studied those also with the Murray Lab, who's made those. You can have assemblies where you can put optically or thermally addressable ligands, and you can geometrically change the assembly. So it should work if we can get it to the processing steps to all work. Yeah. Not yet.
Okay, if there are no further questions, please join me in thanking Cherie again.